Okay. So there is someone out there listening. Please respond, and not the usual
Yes,
people.
sir.
Also people who don't usually respond, because it's very important that I get a feel that there is someone to whom all this is useful. Okay, if you don't speak up, and not the same set of people, others as well, because this is, I want to get a feel that yes, all these hard work that we are doing is benefiting people. Otherwise we can all read the book. So please, not just one fixed set of people, also others speak up sometimes in the class. Okay, so so has anyone not looked at the homework problems yet? So basically I assume that everyone has at least looked at them, if not solved all of them. So on the Friday meetings, we have tutorials. So please do come for that. And I think people found it useful. So there were like 6-7 people this time, and I think they found it useful. So that will also become more streamlined with every session. Okay, so I'll start sharing my screen. Oops. No, not this screen. Just a sec. So that would be the desktop. Okay, so you can see what I'm showing. Okay, and so the other thing that I figured out last time was that we were not able to. I was not able to save it on the same class notebook. So I will actually create these sort of chapters by date. So that will also make the size of this thing small and make the screen more responsive. Okay, so let's get started. Okay, here. Okay, so last time we covered so we finished till radiation force, right? So if a material absorbs photons, the photons transfer their momentum to the material, so the matter feels pressure due to radiation passing through it. So that's called radiation pressure. Okay, so today we'll actually do a little bit of thermal radiation. Okay. So thermal radiation. So let me go here. So the topic is thermal radiation. Right. So thermal radiation is not synonymous to black body radiation. So thermal radiation is more general than black body radiation. Right. So thermal radiation is radiation emitted by matter in thermal equilibrium, right? So if you have, say, for example, the gas in the atmosphere is in thermal equilibrium, right? If you look at their velocity distributions and the energy level distributions, they follow the Maxwell-Boltzmann distribution. So this is matter in thermal equilibrium. And feel free to interrupt me if you have any questions. So basically, the radiation emitted by such matter, which is defined by some temperature T. This is the temperature of the matter, okay, which is radiating. Such a radiation is called thermal radiation. But thermal radiation is not the same as black body radiation. So so when does the thermal radiation become black body? If So photons are in equilibrium with matter, right? So that's when the thermal radiation becomes a black body, the universal black body radiation. Okay. Right. So is this distinction clear? So thermal radiation is a superset. And when photons are in equilibrium with matter, that's when you have black body radiation. So when is matter in thermal equilibrium? When, when particles collide frequently and achieve Maxwell-Boltzmann distribution. Right, so this is only about the particles, not about photons. Right, so the particles are well described by a temperature T in that case. Right, if they are able to collide with each other, they achieve a Maxwell-Boltzmann distribution of level populations, for example. And when does matter, when does the radiation coming out of such matter become black body? The condition for black body is that photons are able to collide frequently with matter, right? So the matter itself is in equilibrium, but photons are also in equilibrium with matter. So that's when black body radiation is achieved. So right, the high school picture that we have of black body radiation is you take an enclosure and put some photons in that, and they sort of collide with walls, and they relax, and you make a hole in it, and sometimes these photons which leak out of this hole, they will be distributed according to this black body. They will have a universal black body radiation. Okay, so this is very, very important to distinguish between thermal and black body radiation. Okay.
Sir, so I mean,
Yes.
both will give the black body spectra, right?
No, no, no. Thermal radiation is not necessarily black body.
Okay.
If the matter is optically thin, thermal radiation can be very different from black body radiation. So examples of thermal radiation are, for example, line emission, right? If you see, some optically thin dilute gas emitting, it can have a lot of lines, right? But black body radiation does not have any lines. It's perfectly smooth, right?
Yeah, correct. Yeah.
So that's the distinction actually.
Okay.
But thermal matter will have, is matter which is in equilibrium. That's it. So black body is more special.
Okay. Thank you.
Okay, good. So photons are massless, and they can be absorbed and created by collisions with the wall, right? So this is another property of photons. It's very easy to create and destroy photons because they are massless. There is no mc squared required to create or destroy photons. And photon number is not conserved, right? Normally, if you take a gas in a box, the number of particles is conserved. But since photons can be easily created and destroyed, the photon number is not conserved.
Sir?
Oh, yes.
So in this Maxwell-Boltzmann distribution of the particle.
So actually, please speak your name as well so that I know who is there.
Ritesh. Yeah.
Okay, Ritesh. Yeah.
Yeah. So I'm asking that the Maxwell distribution of the particle is actually like when the black body when the thermal equilibrium is actually black body radiation,
Right.
then only Maxwell-Boltzmann distribution is happening, or is it always this?
No. So when the matter is in thermal equilibrium, right, the matter has a Maxwell-Boltzmann distribution. For example, atmosphere, right? Earth's atmosphere. Just a second, I have a noise in my I told these guys not to do this drilling work. Give me a sec, I'll just tell them and come back, huh? Otherwise, this is really annoying me. You can hear this noise, right?
Yeah.
Yes.
Just a sec. Yeah, looks like he'll go in a bit, but you know. Hello. So yeah,
Hello.
Ritesh, yes. So you had this question about Maxwell-Boltzmann, right? So for example, the atmosphere, the air in the atmosphere, right? It is in equilibrium because collisions are very, very common among particles. So the velocity distribution is Maxwell-Boltzmann. But the photons, like the light from the sun is not, so the sunlight that we receive has a temperature of 6,000 Kelvin, right? Which is the surface of the sun. Our Earth, you know, the atmosphere temperature is about, you know, whatever, 300 Kelvin, right? So this matter in the atmosphere is in thermal equilibrium, right? But this is not emitting black body.
Yeah.
Right? If it were emitting black body, it should have been at 300 Kelvin. The radiation that goes through the Earth's atmosphere is the sun's radiation, which has the black body temperature of the sun. So Earth's atmosphere is an example where matter is in thermal equilibrium. So it's a thermal emitter, but it's not black body.
Okay.
Right? So this is the whole reason we put these tanks for heating at top of our roofs, right? We put these tanks for water to get heated because the photons which are absorbed are much hotter than the atmosphere.
Yeah.
Otherwise, we cannot, use that, right?
So my question was a little bit different. So I was asking that whether this Maxwell-Boltzmann distribution,
Yes.
like, so what distinguishes between the black body radiation and thermal thermal radiation?
Right.
Apart from that, you know, the emission example that you gave.
Right. So, basically, black body radiation. So, an example of thermal radiation is like, you know, radiation because of atomic lines.
Sir,
Right.
I think in case of the black body radiation, the
Who is this?
distribution
Who is
is. Sir,
speaking?
this is Aratrika.
Yes, Aratrika.
So in case of the black body radiation, I think the distribution is Planck, unlike Maxwell-Boltzmann distribution of the.
That is correct. That is correct. I mean, the black body frequency distribution is Planck distribution. That's correct. But what I'm saying is, even if you have a thermal radiating gas, its photon distribution is very different from Planck. That is correct. So you know you can have free radiation, atomic lines, bound free radiation. So most of these radiations are thermal radiations, but not black body because they are not optically thin, right? This condition means that matter is optically thin.
Sir, but for example, if there is enough, this is Kinjal, by the way. So if there is enough thermal, I mean, if there is enough optical thickness,
Yes.
so will that spectra also tend towards a black body?
Absolutely. Yes.
Okay.
So this is the main difference actually. A thermal emitter becomes black body when it's optically thick. We'll actually come to that. Okay. And a good example to remember is Earth's atmosphere. It's thermal in terms of particle velocity distributions or energy level populations, but it's not black body because photons are not in equilibrium. You know, for example, the sun's photons are not equilibrium in the atmosphere. And also the emitted, you know, the atmosphere emits its own photons, but they also have small mean free, long mean free path. So that's why the atmosphere is optically thin, right? You know, a photon produced will just escape rather than interact with other particles nearby. Okay, so yeah, this will actually become clear as we move on. Right, so the other thing is black body radiation is universal, right? Whether the, you know, whether it's produced by, you know, sodium lamp or, you know, coal burning or a very hot rod of metal, it's the same. It only depends on you know, so the specific intensity is universal, which is denoted by B nu T. It only depends on the temperature of the black body and nothing else. Okay.
So sir, this is Kinjal. One question.
Yes.
For example, sodium will have this, I mean, only particular frequency, right? I mean, only
Yes.
at particular frequency. So there will be kind of a line spectra.
Yes, that's when it is thermal spectrum.
Okay, but even sodium gives a black body.
Yes, if you have a huge collection of sodium and if you ignore the atmosphere around that collection, it will be black body, like stars, right? The continuum in stars is black body, but there are these absorption features which come because of the atmosphere, you know, the optically thin layer above the black body.
So if, for example, if in a lab, if we heat sodium high enough, it will give off a black body spectra.
And if you have enough of sodium, right, you need optically thick sort of column
Sodium.
of
Oh,
sodium.
yes. Okay. Yeah, sure. Thank you.
Okay, so that's the main thing. So this drilling has again started. Okay, he said that it will just take 5-6 minutes. Let's see. Okay, so black body radiation is universal. It only depends on temperature. It is also isotropic. So specific intensity for a black body does not depend on direction of photons. Right, so it's I nu, or which is B nu, which only is a function of temperature. Okay. Now, if this was not the case, if it was not universal, right? So you can actually arrange a black body at a temperature T here and a temperature T here, and suppose at some frequency the amount of radiation coming is not the same, right? And then you sort of connect these with that filter, with the frequency at filter where the two are not emitting equally, then you will have energy transfer between these two, right? Suppose here, let's say I nu 1 is greater than I nu 2, you know, I mean basically I nu here is greater than I nu here, and these both are black bodies, then you will have, you know, photons will go from here to here, and that means you will have you will transfer energy between reservoirs at the same temperature, which is not consistent with laws of thermodynamics. In the same way, if black body is not isotropic, then you can actually connect them. You know, suppose you have a black body here and it's emitting. If this direction had some other, and this is sort of like the normal, if this direction had some other spectrum, then you can actually connect a black body here, which is normal, and then you will have energy transfer between bodies which have the same temperature, which is against thermodynamics. So that's why the black body universal spectrum depends only on temperature, not on direction, not on the material properties of the body. Okay, and it has the same energy of photons coming out at a frequency nu. Okay, so that's why it's very, very important. So it simplifies, you know, the black body assumption simplifies our life a lot. We don't have to bother about microscopic details. Okay, so this is this. Okay, so now we are actually coming to the radiative transfer aspects of thermal emitters. So Kirchoff's law, right? So this is called Kirchoff's law, right? Kirchoff's law basically says that S nu, right? If you remember S nu, the source function in our radiative transfer, we did source function for a thermal emitter is equal to B nu T for a thermal emitter. So basically this is an emitter which is in thermal equilibrium. Matter is in thermal equilibrium. It is not black body, right? It's not black body, it's just the matter is in thermal equilibrium. So this is Kirchoff's law, and we know that, so basically, right, so this implies that J nu, the emissivity or emission coefficient J nu equals alpha nu B nu T, right? You remember the definition of S nu was J nu divided by alpha nu. So this is emission coefficient and this is absorption coefficient. So this Kirchoff's law states that an efficient emitter is also an efficient absorber, right? This is actually very true, and you must have read this in your textbooks as well. And this is the reason for that. This is the emission property. This is absorption property, right? So if you have a material which absorbs well, it will also emit well. And the reason for that is Kirchoff's law, that which is this, right? And we can actually see why this has to be true. We know the radiative transfer equation is given by d I nu by d tau nu. So this is our radiative transfer equation, equals minus I nu plus S nu T. But for a thermal emitter, S nu T is just B nu T. Right. So this is the radiative transfer equation for a thermal emitter.
Sir.
Yes.
So
yes.
this is Amlan. So here B nu T. Amlan. Sir.
Amlan. Okay, please.
Sir, here B nu T is it Planck distribution function or something else?
This is Planck distribution function. Yes, B nu T is the Planck distribution function. Yes, absolutely. Okay. This is the Planck function.
But you said this is thermal emitter, not a black body. Then how it is?
No. Right. So this is thermal emitter. Right. So okay. So I'll actually explain that. I'm coming exactly to what I'm saying is for a thermal emitter, S nu equals B nu. I'm not saying I nu is equal to B nu. There is a difference between S nu and I nu, right? Yeah. I nu approaches S nu when you are optically thick. If you remember your radiative transfer equation. So that's it. And this is all consistent with what I said. So what is the solution? We know that the solution is I nu. Nu equals I'm assuming that there is no background radiation, there's only self-generated radiation. Let's just B nu T 1 minus e to the minus tau nu, right? This we did last time. This is the solution for this simple radiative transfer problem. And what does it mean? For tau nu is much less than 1, what do we get? we get I nu is equal to tau nu B nu, and this now this will depend on all the details of absorber or emitter, right? In terms of this, right? But when tau nu is much bigger than 1, what do we get? I nu equals B nu T, right? Which is black body. This is not black body, but thermal. Got it? So here, because of this tau nu complicated dependence of absorption and emission on the material constituents, this will depend on the matter content. Got it, Amla?
Yes, sir. Yes, sir.
Good. So I think, today this was actually a good idea to create a new class. Let me go to the next screen. As I said, I am also still trying to figure out all this technology. Okay. Okay. So good. So this is Kirchoff's law. Right. So so Kirchoff's law says that the invisible man, right? There can be no invisible man, because or if you have an invisible man, he cannot see what's happening around him, right? If you have invisible man, that means you do not see that person. So it's so. Let me get back to this. So invisible man means that J nu is 0. If J nu is 0, and if that invisible man is sort of made out of thermal material, alpha nu will also be 0. That means it will not be absorbing anything. So if you have an invisible man, it cannot absorb anything, so it will also be blind. So it cannot perceive anything by radiation from its surroundings. Anyway, that's an aside. But you understand the logic behind this, right? Invisible man has J nu, which is 0. It does not emit anything. So its alpha nu will also be 0 if it is made out of matter in thermal equilibrium. From Kirchoff's law. This was a question that some professor asked in a comprehensive exam that I was sitting in, so I thought it was interesting. Okay. Let's see. So black body radiation is homogeneous, isotropic, and if radiation is isotropic, we know that isotropic radiation implies that pressure, the radiation pressure, is equal to energy density divided by 3. This we derived in one of our previous classes. So this just assumes isotropic distribution of photons, so that I nu can be taken out of that integral, and all you have is this cos squared theta. Okay. Now, what is the black body radiation? Black body radiation, I nu equals B nu. And what is thermal emitter? Thermal radiation is S nu equals B nu. This is the difference. Okay. Not necessarily I nu. Okay, now I know. As there is more and more material on a slide, I start experiencing lag. So we will not have more than one class on this whiteboard. Okay, good. What else? Right. So we know a lot of things about black body radiation already, and there are some thermodynamics. So from thermodynamic arguments. For example, this one. So using this, we can actually derive the following laws. This is done in the book, but I'll actually not do it. It's actually simple. We'll derive the following important properties of black body radiation. So UT is equal to a t to the 4, right? So this is the energy density of radiation in a black body, right? This you all know. In fact, not this one. We actually know the other guy more, that which is the Stefan Boltzmann law, right? The flux, right? The flux emitted by a black body, flux is equal to sigma t to the 4, right? This everyone knows. This is called Stefan Boltzmann law. Right? These can actually be derived from thermodynamic arguments, right? The first law of thermodynamics, and using this relation between pressure and energy density. Okay, now this A, this A is called radiation constant. This sigma is of course called Stefan Boltzmann constant. And we, if you recall our definitions of various quantities, U, right? So the energy density U equals 4 pi by C integral B nu T d nu, right? You recall this? What is, so this is the energy density integrated over all frequencies. This is specific intensity for a black body, right? So if you recall, U was nothing but 1 by C integral I nu d nu, and if you recall, we also had this specific we had defined this something called a mean intensity, right, which is 1 by 4 pi integral I nu d omega. So this was called mean intensity. And this is of course there's also an integral over all solid angles in this one. This is energy density. So because of these, from these relations we get this, the relationship between energy density of photons in a black body and the and B nu function, specific intensity of a black body, right? So we can actually see, right? And I mean, there was a homework problem where so this was where I wanted you to show that the flux emitted by a isotropic emitter equals pi times I, right? So this is from homework. I don't remember the number homework set. This is from homework. So I had asked you to prove that if you have an emitter, a spherical emitter, and if you're observing it from some distance r, you can actually prove that the flux at a distance r is equal to pi times the specific intensity. So this is an isotropic emitter, and it sort of emits specific intensity I from all points in all directions. Okay, so the flux sort of measured here will be just pi I times, and if this is, say, if its radius is a, pi I times a by r the whole square. So this is what I had asked you to prove. So if you put r equals a, if you're sort of observing right at the surface, then you get pi I. So this is the relationship between flux and intensity. So if you can actually just use this, and this, you can actually find the relationship between A and sigma. Let's see. So F equals sigma T to the 4. This is equal to pi times B, right? I becomes B for a black body, B. But B is nothing but, so this B nu d nu is called B. Right now, because we have integrated over frequency, but it is still a function of temperature. And B is nothing but pi times B is nothing but Cu by 4 pi. So basically, what it means is that U is equal to 4 sigma by C T to the 4, right? So you can actually see this is the radiation constant. So this is equal to A. So, you know, it's useful to recall, you know, as I said, knowing these values roughly helps. So sigma in CGS units is 5.7 times 10 to the minus 5. You know, you don't have to write this unit, so this is in CGS units. You can easily calculate what are the units. And similarly, A is like 7.6 times 10 to the minus 15 in CGS units. You know, it's useful to have a sense of these units. Okay, good. So let me see. Okay, so now here is a quiz. I think I'll ask you. So can you tell me what are the units of this constant A? Can anyone here tell me the units of A? So this is what you would like.
It's like joule per.
No. I don't like SI units. Don't forget about joule.
Okay. I mean,
use erg.
Erg. So it's like erg cm cm to the power minus 3 and Kelvin to the power minus 4.
That's good. So this is erg, right? So this U has units of erg per centimeter cube. So this is erg per centimeter cube. And then you have T to the minus 4, which is Kelvin to the minus 4. So this is these are the units for A. And similarly, sigma will be, right, so A and sigma are related like this. So there is an extra C. Right, so sigma is sigma is A times C. So you just multiply this by centimeter per second. So this becomes erg per centimeter square per Kelvin to the 4. So there was per second, right? So this is sigma and this is A. So you should be very, very comfortable with units. Anyway, I am sure you all are. Okay, good. So this is about the macroscopic properties of black bodies. This everyone knows. I'm sure this guy, Stefan Boltzmann, everyone knows. Okay, what about Planck spectrum? So this is these considerations were thermodynamic considerations. We had integrated over all frequencies. But what about the Planck spectrum? So Planck spectrum. So Planck spectrum basically B nu T. We want to know how is the specific intensity of a black body varying as a function of frequency. Okay. This we need to motivate now. Okay. So let's see. Let me create a little more space. Okay. So how do we calculate what the Planck spectrum is? So it's sort of like a standard statistical distribution derivation that we do in a course in statistical mechanics. So we first find number of states per unit volume. Okay, we have number of states per unit volume for photons. Okay, what's that? Okay, now I'm starting to have that problem again. So what I'll actually do is I will create a new okay new page. New page, and I'll write here, because the computer actually slows down. My pad slows down when there is a lot of. So this is where I'll start Planck. Okay, now it's very nice. Planck, the Planck function. So B nu T. See, now I can write really, really well. This is what we call learning. I learned that. So 19th October number 2. Okay. Okay. So we have number of states per unit volume. So let me just write 2 times d volume in phase space divided by d3x h cube. So this is the number of states per unit volume for photons. So I like actually explain what all this is. Number of states per unit volume for photons. So dVph is the phase space volume, d3x is the spatial volume, and h cube is the elementary volume in phase space. Okay, so what is dVph? dVph is nothing but 4 pi, assuming isotropic momentum distribution, we can actually write it like this: dp d3x. This is the phase space volume that we are considering, and we know that P is equal to h nu by c for photons. So there is a 1-to-1 mapping between P and nu. So this phase space volume becomes 4 pi h by c cube nu squared d nu d3x. Okay, so this becomes number of states per unit volume for photons becomes 2. So this 2 is because of 2 independent polarizations of light, or you can actually call this spins. So spin of photon is equal to 1. So you can have +1 or -1, which are identified classically with polarization. So this is the degeneracy factor. Okay. So every state can have two, every point in phase space D3x, D3p can have two photons. Either with with one polarization or the other. Okay, so this is equal to 2 times nu squared by c cube d nu times d omega. So I'm actually, I'm just calling 4 pi as d omega if we are sort of considering small solid angle. Okay, so this is number of states per unit volume. These are the states available for us to put photons in energy range nu to nu plus d nu. Okay. Now what about so this is A states per unit volume. Now what about average energy of photons over all states? So average energy of photons over all states. You recall some history that derivation of Planck's function, right, imposes upon us the fact that photons have energy E equals h nu. Only with this, a photon of frequency nu has energy E h nu, right? So this is actually forced upon us because of this Planck distribution that is observed. Okay, so so basically this is how you sort of consider this derivation. You consider these states. So n equals 0, 1, 2, 3, 4, and so on. So so if you have if you are in third state, for example, you have 3 photons with energy h nu each, right, and so on. So En in the nth state is equal to nh nu. So energy of photons in the nth state is nh nu. But you also recall that the states with higher and higher energy have lower probability, and that probability is given by e to the minus beta En, right? So this is the Boltzmann factor. Right, so this is actually Planck's quantum, this assumption, right? That if you have n, if you are in nth state, you will have energy En equals n times h nu, where h nu is the energy of an individual photon, of a single photon. Okay, so we can actually calculate the average energy. So there are many ways in which you can actually do this calculation. This is more classical calculation. You can actually use, grand canonical ensemble and whatnot, right? There are many ways in which this calculation can be done. So this is the mean energy, and this is nothing but summation over n equals 0 to infinity En e to the minus beta En, right? And recall that beta we identified as 1 by kBt, right? So this is just, Planck's factor. Okay, so this is the average energy, n equals to 0 to infinity e to the minus beta En. Okay, right, and I mean, this is sort of like partition functions, right? So this denominator is like partition function. So any people who have done statistical mechanics, you can actually easily see that this is why partition function is so fundamental. You can derive all thermodynamic quantities from them. So So for example, here the mean energy we can get by, let me just write down the expression first. So this is the partition function, the log of sigma n equals 0 to infinity e to the minus beta en, right? So this guy is called the partition function. No, sorry, the thing inside the log is called partition function, if I recall right. This sum, oh, so this denominator, this is the partition function. So this is log z. Just a sec. Okay. Now, so how do we see that? If you take dou minus dou beta of log of that, so log, when you take a derivative, you have 1 by the argument, which is this, and then you take beta derivative of the inner summation, and that, if you do dou beta, it pulls down minus en, and that's why you have a negative sign. So this is just simple mathematics. Okay. Okay, good. So now what about okay, so, and we know that En equals nh nu. So what we have is partition function is equal to summation over n equals 0 to infinity e to the minus beta h nu n, right? And this is nothing but this is this geometric series. So right, so this is 1 plus e to the minus beta h nu plus e to the minus twice beta h nu, and so on. This is a geometric series with the amplification factor of e to the minus beta h nu. So this sums to be 1 over 1 minus e to the minus beta h nu, right? This is the sum of this geometric series. Now, if we calculate this, so E bar, what will be E bar is equal to minus dou beta of 1 minus e to the minus beta h nu inverse, right? If you just do this carefully, what you will get is h nu by e to the h nu by kt minus 1.
So there is a ln z, right?
Sorry. Yes. There is a log here, otherwise you will not get it. Yes, thanks. Right, so if you do that, you will get this, right? Now, this has a nice interpretation, right? So this is the mean energy summed over all states for photons. This is the energy of a particular photon, energy of photon at frequency nu, and this eta nu, which is equal to 1 by e to the h nu by kt minus 1, is called mean occupation number of photons, right? So this is the energy of a photon. This is the mean occupation. So mean occupation number times the energy of the photon is equal to the mean energy of photons over all available states of these photons. Okay, so now we come back to our calculation that we were doing. So this is the first step. We calculated the number of states per unit volume. This is the E bar is the energy, average energy integrated over all states. So in the end, we want to get to right, and this right. And I mean, if from statistical mechanics, we actually know, right? If you have things called fermions that have eta is equal to 1 over e to the e minus ef by kt plus 1, right? So this is the mean occupation number for fermions, photons being bosons. The mean occupation number is eta equals 1 over e to the E minus mu by kT minus 1. So this is for bosons. So you can actually see this eta is always less than or equal to 1 or greater than or equal to 0, right? Right, because fermions satisfy the Pauli's exclusion principle. So you cannot put more than one fermion in a single state, whereas bosons have no such restriction. So eta can actually be, can be anything, right? So this is actually a key. So you can actually see this expression reduces to that when mu is equal to 0. Basically, the chemical potential or the penalty for creating photons is 0. Photons are massless. So that's the interpretation of this. So they can be easily destroyed or created. Okay, good. So let's go back to our calculation. Okay, so let's see. Now I want to write U nu omega, right? So this is energy per unit volume, per unit frequency, per unit solid angle. Right, so this is our energy density is equal to, let me just write it. So this would be eta nu times h nu. So this is the mean energy that we just calculated just now. And eta nu h nu is the mean energy times twice nu squared c cube by c cube. Let's go back a little bit and see how you get this. Right, so this expression here, 2 nu square by c cube d nu d omega is the number of states per unit volume for photons. This is E bar is the energy over all states for the photons. So, and you see these d nu and d omega we have actually divided by. So you can actually do this d nu d omega. So you can also multiply this by d nu d omega on both sides, d nu d omega. So you have this as your u nu is this. Right, now we can actually just read off this expression. So u nu, so the energy density for black body from these considerations is equal to twice nu squared by c cube h nu by e to the h nu by kT minus 1. Okay, so let's actually recap. So this was degeneracy factor. This nu square d nu was related to the volume factor in phase space. This h nu was the energy of a single photon. And this factor was the mean occupation number, right? So it's actually very easy to write it down once you know these various elements in this. So this factor of 2, this nu square d nu, h nu, and 1 by e to the h nu minus h nu by kT minus 1. So this is your u nu in a black body. The energy density in photons stored in a black body of a temperature T. Actually, this is only a function of T and nu. You can actually see it. There is nothing else, only nu and T. Okay, and we also know that B nu, which is the specific intensity, is equal to C times U nu. This we know, right? because U nu is per unit volume and B is per unit area per unit time. So these are just differing by a factor of C. So this is the Planck function. So this, let me write down. So twice h nu cube by c squared 1 over e to the h nu by kt minus 1. So this is the celebrated Planck function. This is Planck function. And as you can see in the sort of classic derivation that I showed, it imposes upon us this, which is that you have to assume that photons have energy h nu, and they are quantized. You have n h nu in each state. So this is how, for the first time, Planck, in order to sort of get the experimentally observed distribution of photon energy from a black body, he sort of invented quantum mechanics, right? So this is when the first time he introduces this constant h, which we call Planck constant now. Okay. Now, what are the so any questions on this? Otherwise, I can actually move on to. I mean, this is all good stuff. You should read it up in statistical mechanics books. The stat mech is a really, really powerful subject to treat, bulk properties of material from more fundamental viewpoint, of course. Okay, so let's go back to, let's get to some properties of black body radiation. Okay, so let's see. Rayleigh genes regime, right? So Rayleigh genes regime is this classical regime when you have h nu by kt much less than 1, right? What happens in this case is I nu Rayleigh genes. If you look at the Planck formula, and if you just expand it for h nu much less than kt, you have 2h. So this just becomes twice kt nu squared by c squared, or this is equal to twice kt by lambda squared, right? Because lambda is equal to c divided by nu. So this is called the Rayleigh genes law. And this h Planck factor actually gets cancelled from above and from below. So there is no Planck formula in classical laws. And in fact, the interpretation of this is also quite straightforward, that this is the number of degrees of freedom, which is proportional to nu square, the phase space volume. And then every degree of freedom has kt by 2, right? E bar equals kt. So this is sort of that every degree of freedom has energy kt by 2. This can be interpreted like that. Of course,
sir, I think kt by 2 for non-relativistics only.
That is correct. Actually, we are considering photons. So just a sec.
It can be kt, right?
So here you will have, yes, that just comes from half mv square, right? So if you consider kt as sort of energy in every degree of freedom, you have 2 polarization degrees, and you have this nu square as the volume in phase space. So you have this formula, but the problem with this is as you go to higher and higher frequencies, it goes like nu square, and there is a UV catastrophe. If you basically the problem is I nu rj d nu. If you just do this, this is nu max. It goes like nu max to the power of, how would it go like? So nu square, so minus, right, it's cube. So nu square d nu. So basically this blows up, and that cannot be physical, right? So at high frequencies, you have to, at high nu, must consider the discrete nature of photons. That is, energy can only be h nu for a given photon. So if you go to very, very, very high energies for very, very, very high frequencies for a given temperature, the number of photons becomes exponentially small. You cannot have many, many photons. So that you have to be careful about. So this is Rayleigh-Jean's law. And this is valid when you're looking at frequencies smaller than kT, h nu smaller than kT. So then there is Wein's law, Wein's regime. In this case, you are in h nu much greater than kT regime, and if you look at this Planck formula in that limit, you get I nu Wein is equal to twice h nu cube by c squared times e to the minus h nu by kT. So this gets this exponential factor correctly, this exponential fall at high frequencies due to discreteness of photons, right? So the number of states sort of keep increasing, but there has to be another factor here which accounts for the fact that the number of photons at that high frequency should fall, and that's this factor, Planck factor, this occupancy factor, that the occupancy becomes smaller and smaller as you go to high frequencies. Mean occupancy. So okay, so this is Wein's law. C is so B nu T is monotonic with temperature. That is, if I draw the black body curve on a log, this is log, so this is B nu, this is T, this is nu, B nu for a given temperature. If I plot B nu for some other temperature, it will always be above. So this is higher temperature, so T2 greater than T1. So basically B nu at any frequency will be higher for higher temperature. You can actually show this. Okay, D. So Wein's displacement law that h nu max is equal to 2.82 kT. Right. So this function that I have shown, B nu as a function of nu, it will reach a peak value at 2.82 kT. This can also be just shown by mathematics of this function, right? You have B nu as a function of nu. You just take dou B nu dou T dou nu equal to 0. That will give you the maximum, and you can actually numerically solve it and get where the maximum occurs. So this is what you can actually show. So this is sometimes used to infer the temperature of the star from the observed frequency distribution of radiation from it. So this is related to the concept of color temperature. Okay, what else? And you can actually get these radiation constants, so sigma and A can be obtained in terms of fundamental constants, Boltzmann constant, Planck's constant, and speed of light. Okay, and it's instructive to do these. I'll not do them in here. Now there are also temperatures associated with emitters. So sometimes instead of dealing with intensity, we deal with temperature, and there are like various temperatures associated with emitters, and I'll actually quickly talk about them. So first, say color temperature. Okay, color temperature is defined such that the intensity that you're observing is equal to B nu TB. So you're observing some source at some frequency and you measure its specific intensity I nu. Okay, you assume that it's a black body emitter and you fit. So you fit B nu. At what temperature does this specific intensity is produced by a black body? And that you call its color temperature. Oh, sorry. Not, this is not color temperature. This is called brightness temperature. I'm sorry about this. Brightness. That's why B. Right. So, and it actually makes a lot of sense in the Rayleigh genes part, because in the Rayleigh genes limit, I nu equals twice nu squared by c squared kt. Right. So, if you define I nu equals, so I nu is proportional to the brightness temperature in the Rayleigh genes limit. So I, which is a little more difficult quantity to sort of relate to specific intensity, you can actually deal with this brightness temperature. But you have to be careful. Brightness temperature is not the same as temperature of the black body. And this brightness temperature can be associated with even a non-black body emitter. So it's very frequently used in radio astronomy, because the radio emission is generally in the Rayleigh genes limit. So if you can actually write the radiative transfer equation in terms of the brightness temperature in the following way: dTB d nu is equal to minus TB plus T. Right, so this TB is just like I nu. So d I nu by d, so d tau I tau nu. So d TB by d tau nu equals minus TB plus T. So this is sort of like a specific intensity. TB is like a specific intensity, and T is like the source function. So this is the temperature of thermal emitter. So you will see a lot of radiative transfer actually done in terms of the brightness temperature. Brightness temperature. Okay. So this is one thing. What else? And of course, this can also be solved just like the radiative transfer equation. So the other concept is color temperature. Color temperature means that it's based on basically applying this KTC is equal to 2.82 H nu peak. So if you see, for example, a star, and if you see that it peaks at some frequency, so if you look at a stellar spectrum and you sort of are able to capture this peak, so this is log again, and this is this is I nu, or the flux as a function of frequency, and you are able to measure at what frequency is the radiation peaking. So if you know the peak, you can actually get the corresponding black body temperature, and that temperature you call color temperature. Only for a black body, color temperature will be equal to the black body temperature. If you have some other radiator and it has a peak, this is just the definition of color temperature. Color temperature is based on frequency spectrum, basically, specifically peak. Okay, this is color temperature. The third and the final thing that I'm going to talk about today is called effective temperature. Effective temperature is defined this way. So flux is equal to cos theta. This is just the standard definition of flux. I nu d nu d nu d omega, right? This is equal to sigma T effective to the 4. So basically what you're saying is all the energy that you're receiving, all the flux that you're receiving, which is emitted by the black body, is given by sigma T effective to the 4. So basically this is defined in terms of energy output across all frequencies. Okay, and if you have a black body emitter, then all these three definitions will agree, all the same for black body emitter, right? Why would they all be the same for a black body emitter? Because for a black body emitter, right, for a black body emitter, TB goes to the temperature of the thermal emitter, which is nothing but the black body temperature. A black body will always peak at this frequency given by this Wien's displacement law, and the effective temperature of a black body is also given by the Stefan-Boltzmann law. But if you have a non-black body emitter, these can be quite different, so one has to be careful. Okay, so I think this is all for today. Okay, so I'll end the class. If there are any questions, you can ask me now.
Sir, this is Kinjal.
Yes.
So say we say that this, like for sun example, we can, generally we see the surface of the sun. So
Yes.
we say that this 5800 Kelvin, the figure is for the surface brightness. So it is here the T effective.
Yes.
And
But no,
it is equal to
for the sun, right. So if you say that, oh, the sun is peaking at this, yellow frequency, right? So that would give you, the easiest thing for star is the color temperature, right? Because you know the color of the star. So whether it's blue or is it red or is it green, right? Color gives you at what frequency is it peaking.
But
So,
see, color temperature is, I think, for the temperature we receive. Say for example, there is a very far away source.
yes.
Their color temperature is, for nearby stars we can use color temperature, but not for far enough stars.
What do you mean by far? Are they at cosmological distances?
Yeah.
Yeah, of course, but
redshifts.
Yeah. This is all classical astronomy. Redshift is a very recent idea. All these things have been used in the 18th century and so on, right? So the color temperature and have been generalized now. So we are actually talking about nearby objects. Of course, if you take the sun and put it at a redshift of 1, it will no longer be peaking at yellow. It will become red, right? If you are able to see it. So yeah, but this is all based on things which are nearby, specifically actually stars.
Okay. Thank you.
Okay. All these things are actually used in some particular context. They are all. The fundamental thing is I knew. These are all like convenient ways of describing radiation when you make some assumptions. Okay. This is more astronomy. This is more like jargon in some sense. This is what, if you look at some literature, Say if you read some literature on stars, you may come across color temperature. If you look at 21 centimeter radiation transfer, epoch of reionization and so on, you will see a lot of this equation. Right? And if you're looking at accretion disk theory, for example, where you're not so much, where you're sort of just looking at global energy arguments, you will encounter the effective temperature. Okay, so these are all very these concepts are used in a very specific way normally, but it's good to know them. Okay, so I think today's class was fine in terms of the technical issue. So what I have realized is that if I do more than one page of this, the writing at the end starts becoming really bad. So what I'll do is I'll create more and more pages rather than add on to the same page. So this is what I've learned. Okay, and these are all in actually here. So in the content library, I'll just create October 19 and date wise I'll put them. Okay. Okay then. See you in the next class.
Recording, I think.
Yes, yeah, that's actually something. Yeah, thanks a lot. I should stop recording and then okay, bye bye. Okay, bye.